What is the system response if t of s is equal to s plus 2 over s plus 3 and the input is a unit step? Now this is a time response, of course. So we can solve this problem by drawing the pole zero diagram, as opposed to, like, if it was a frequency response, for instance, then would have to deal with the gain and the number of decades or octaves or whatever. But this is time response, and the input is a unit step. Now for the input, it could have been anything else. It could have been impulse, it could have been ramp, it could have been an exponential system. Doesn't matter really, but so pay attention to the question, really. So here it's a unit system. So the transform of a unit system is 1 over s. Now you can go to page the old book. I have the old book, but the PDF, I don't know what page is that, but it's that particular page where they have the Laplace transform, and you could clearly see on the table that the transform for unit step is 1 over s. Now the total response, the system response, we can call that r. Let's call that r of s, and the unit step, let's call that maybe I of s or something. So the total response will be t of s multiplied by the input, let's call that I of s. Okay, so now the input is a unit step, so that's 1 over s, and so when we multiply those two together, it will give us 1 over s times s plus 2 over s plus 3. So this is just we can get rid of the 1, s plus 2 over s times s plus 3. Okay, so now we can draw the pole zero diagram. So what's our the zeros would be the top, the numerator, and then our poles would be equalizing, if that's a word, the denominator to 0. So r0, we only have 1 0 here, so that's minus 2, and then the poles would be s equal to 0 and minus 3. And so therefore the pole zero diagram is so we have a pole at a 0, the origin. Let me put minus 1 here, minus 2, minus 3, and we have another pole here, and we have a 0 here. So the pole at r equal to 0, that's contributing to, of course, c e to the power minus 0t, and then the pole at r, we only worried about the pole, so the pole at minus 3 is contributing to c, well, let's call that c1. It's a constant. Now you can find a constant if the problem here is just pretty straightforward and pretty simple, but eventually, if they could have given us some other, I don't know, some other maybe requirements or something like that for us to find c1, but in this particular case we don't have to do that, so we can just call the constant c1 and c2. So we have c2 e to the power minus r t, and as such, therefore, the total response rt, which would be in relation to this, the time response would be rt. This would be little r t, would be the sum of that. So that would be, this is 0, so e to the power 0 is going to be 1, so we only have c1 plus c2 e to the power minus 3. And that's about it. This is the total response. Now, it could have been a little bit more complicated, I guess, but I wanted to show you like how to approach problems like this. Typically, you just multiply out and find your Laplace transforms. Then pay attention to what they tell you the input system is. So depending on the complexity of that, then you could go on and on. But it's not really, it's fairly straightforward, literally. So multiply out and find a Laplace, then that's it. That's your total response. So, all right, if you have any questions or comments, let me know. Thanks.